Hey scholars, welcome to Math Savvy. I'm Stephanie, and today we are going to be continuing our Calc 3 series with a very introductory topic, which is the three-dimensional space. So Calculus 3 is all about it is called multivariable calculus, and that has to do with more dimensions. We're adding a dimension here. It's usually x and y in calculus 1 and 2. We are adding in a z, and a lot of people have trouble visualizing this, so I thought that I would make a video about it and have some examples of lines, spheres, the distance function of r cubed, etc., etc. So keep watching for more. Okay, let's begin. So what is the third dimension in calculus? So instead of 4 quadrants in the 2D space, there are 8 quadrants in the 3D space, as shown here. As for visualizing how we draw the graph, I want you to think about the corner of a room. So the z-axis is going to be the height line, or the line that goes to the ceiling. And then the two floor lines are going to be the x and y axes. That is usually what people reference to when they're trying to visualize the third dimension in calculus, period. So for any point, let's say 2, 1, this is how we could visualize that with the 3D graph. If it's landing on the xy axis, it would be located at 2, 1, 0. Or it could land on 2, 1, minus 10, for example. So it could be anywhere in that z direction. So now let's say we have 2 points and we want to find the distance between them. We love distance, you know what I mean? We have P1, which is 0, minus 2, 5, and P2, which is 2, 4, 0. P2 lands on the xy axis, which is pretty cool because the z value is 0. So let's find the distance, my friends. Let's take the square root of the x value of P1 minus the x value of P2, take that quantity squared, plus minus 2 minus 4. Tis the season for allergies, you know what I mean? Squared plus 5 minus 0 squared. And we get the square root of 65. And this is the general formula that you are going to use for distances. Think of the Pythagorean theorem. Think of how you find the hypotenuse here. So for 2 points, the distance is the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Not too bad, you just need to know the formula. So let's do a problem. Find the distance from 3, 7, minus 5 to the following. Let's start with the y-axis. So I'm going to draw a graph just to visualize this, and we're going to plot the point. So that is the approximate place where the point would land. And we're trying to find the distance to the y-axis. So if you're looking at the graph from that angle, if you want to get to the y-axis, you're going to go 3 units towards the y-axis in the x direction, and then 5 units towards the y-axis in the z direction. And you're going to want to find that blue hypotenuse there. And what do we get? We get 3 squared plus 5 squared equals the square root of 34. Perfect. So that was the intuitive way to do this problem. That's the way that I would do it. However, that is not the way that I just taught you with that distance formula. So this is the way to do it with the formula, and you can decide which one works better for you. Okay, so what we did was find the distance between that point, 3, 7, minus 5, and then we're going to find the point closest to us on the y-axis, i.e., the point where x is equal to 0 and z is equal to 0, and that would land on the y-axis. So what's the point closest? Which is 0, 7, 0. we're going to find that distance. We're going to use that formula. 3 minus 0 squared, 7 minus 7 squared, minus 5 minus 0 squared, the sum of all that, take the square root, and we get square root of 34, which is the same solution that we got in the last problem. So let's do the other three. So the xy plane, that is where z is equal to 0. Do you see a pattern here? Okay. So 3, 7 minus 5, 2, 3, 7, 0. And what is the distance between that? It's just 5 units. You can do the formula and find the same answer, and that's what we get. Similarly, for the YZ plane, what is that? You guessed it. It is where x is equal to 0. So the closest point on the YZ plane is 0, 7 minus 5. And the distance between those points are 3 units. So those ones were easy. So now I want you to try and do the z-axis on your own, and I'll meet you back here, you know? Okay, so what we did, I did it my intuitive way. We're going to count 3 in the x direction towards the z-axis and 7 in the y direction towards the z-axis. And we get the square root of 58, period. Period. Good job, friends. So by now, you've been taking Calc 1 and Calc 2. You are very familiar with graphing in the second dimension, i.e. r squared. So let's add another dimension and graph some lines here. Okay, so x plus y equals 2 is our first example. I'm going to rearrange that so I can easily graph that on the xy plane. And we get something looking like that downward sloping line. Now, converting it to r cubed, we're going to do the downward sloping line in the x and y direction. However, in r cubed, because the z is not mentioned in the initial equation, that means that all z values are included here. Therefore, x plus y equals 2 in the r cubed space is a plane, as I tried to draw here, and I tried my best, so no one's perfect, you know? Okay, moving on. So let's graph z equals 5. And in the x and y space, in the r squared space, it's just everything. Like, we don't know what that is. It's foreign to us, so let's just not even worry about that. In r cubed, it is all of the points such that z equals 5. So it is also a plane here. So it is a parallel plane to the xy plane. And you take the xy plane, you just shift it up 5 units. And I tried to draw again, and I think it's not too bad. What do you think? Okay, y equals x squared. We get something looking like that parabola in r squared. For r cubed, let's try it. So I'm going to get that little curvy looking thing. So it is like a flimsy piece of paper. I'm not sure what I would call that in mathematical terms, but it is a parabola that is turned into a plane. Do you see a pattern here? That is what the y equals x squared function would look like in the r cubed space. So it has all values of z. It moves in the indefinite direction of z. And finally, I drew something special here. I wanted to represent the y equals sine x curve in the r cubed space. So it looks like that little, it looks like a little flimsy paper, and it goes on forever and ever and ever. Although it is limited between -1 and 1 in the y direction, but it goes forever in the x direction, and it spans forever in the z direction. And that is what it looks like in the 3D space. So we can also represent common figures in the 3D space. So for example, we can represent cylinders or spheres, etc. So what does a cylinder look like? We have x squared plus y squared equals 1, which is a circle in the r squared space. However, it is a cylinder in the r cubed space. Anyways, here is my little drawing of the unit circle that turns into a unit cylinder with radius 1, and it goes on forever unless you cut it off in the z direction. And what would that look like if you cut it off? There would just be some sort of limit for the z along with the x squared plus y squared equals 1 equation, and that would make the cylinder cut off in the z direction so it doesn't go on forever. Similarly, we have something that looks like a sphere. It has the equation x squared plus y squared plus z squared equals 1, and it looks something like this, and we call this the unit sphere. Before we move on, I want to cover the sphere a little bit more. And so let's do 2 practice problems. All right, find the equation of the sphere that passes through the origin and is centered at 3, 8, 1. So step 1, we have to find the center and the radius, but we already know what the center is. So my step 1 is to find the radius, i.e. the distance. So r equals 3 minus 0 squared plus 8 minus 0 squared plus 1 minus 0 squared. We are just subtracting the origin by the center. So 3, 8, 1, and that is to find the radius. If we're passing through a certain point, we know that the distance of that point and to the origin represents the radius. So I'm going to take the distance here. I get the square root of 74. And so now that we know the center and the radius, we can just write the equation. So the equation would be x minus 3 squared plus y minus 8 squared plus z minus 1 squared. And that represents the center of the circle. And then all of that would be equal to the radius squared. And what is the radius squared? We know what the radius is. Let's just square it and we get 74. And boom, that's the equation. Good job. The next problem, show that the equation represents a sphere and find its center and radius. So I have this equation here, x squared plus y squared plus z squared minus 6x plus 4y minus 2z equals 11. We're going to manipulate this. And so we are going to complete the square to get it in the form that we just saw in the previous problem. So x squared minus 6x, I'm just going to add a plus 9 there. Y squared plus 4y, I'm going to add a plus 4. And z squared minus 2z, I'm going to add a plus 1. So what did I just do there? The coefficient in front of the first degree variable, we are going to cut that in half and square it to get the number to complete the square. So I took 6 divided by 2, I squared that, 3 squared is 9. And then we can simplify that to be x minus 3 squared. Similarly, we get y plus 2 squared and z minus 1 squared. Good job. What we do to an equation on one side, we must do to the other. So I'm going to add 9, I'm going to add 4, I'm going to add 1. In total, we get 25. So the center would be 3 minus 2, 1, according to this equation. And then the radius would be 5. And what we did was just took the square root of 5 because that is the form that we're in. Great. Okay, let's just do a couple more problems. This time we're going to throw in some inequalities here. So we're going to describe, I'm not going to do it in words, but this is just a textbook example. We're going to describe the region of R cubed represented by the inequality. Let's do the first one. So the first problem is the space in between 0 and 6 in the z direction, not including 0 and 6. So what that is a rectangle. It continues indefinitely in the positive and negative x direction and in the positive and negative y direction. However, it does have a limit on z, which is in between 0 and 6, and it represents all of the points in between that, but not including z equals 6 or z equals 1. Similarly, we have x squared plus z squared is less than or equal to 9. So what did we get there? We got a circle in the xz plane, and that has a radius of 3. So it moves in the y direction indefinitely. It includes all of the points on the shape of the cylinder and within the shape of the cylinder because of that less than or equal to sign. And it continues indefinitely in the y direction, in the positive and negative direction. So yeah, so that would be a circle in r squared, but a cylinder in r cubed. Lastly, we have x squared plus y squared plus z squared is greater than 2z. So let's do some manipulation like we did in that last example. So let's complete the square for the z variable, and we get z minus 1 squared because what we did was add 1 on both sides to get that perfect square. So then we can graph it here. We're going to graph a sphere centered at 0, 0, 1 with a radius of 1. And the inequality represents all of the points outside of that sphere. And the sphere is not included there. So that's all I have for you today. My goal was to just help acclimate you with the 3D direction, and I had fun making this video. I hope you enjoyed it, and hit us up for some online tutoring. That's what we do here. And thanks so much for watching. Thanks for your support, and good luck out there.